Hi, everyone. Thank you for joining and welcome to episode 115, I think, of YugabyteDB Friday Tech Talks, talks by engineers for engineers. I'm Mihnea, I'm Senior Director of Engineering at Yugabyte. And it's my pleasure to introduce today's speaker, Gaurav, one of the core engineers in our Query Optimizer team. So without further ado, Gaurav, please take it away.
Yeah, sure. Let me just say again, I'm Gaurav. I'm working at Yugabyte as a software engineer for the last 2 years. For better part of the last year, I, along with a small team at Yugabyte, have been working to develop and validate our new cost-based optimizer. And we've achieved some significant performance improvements in both single primary and distributed workloads. This new feature has been released for early access in the 2024.1 release, and I'm proud to be here on behalf of the whole team to share the details of this project and then present the results from some of our testing. So perhaps I can start, right?
Yep.
Okay. So let me go over quickly the agenda. So to build some context, I'm going to talk about what is a query planner, also known as the cost-based optimizer or the CBO. Then I'll go to then I'll show a high-level software architecture of YugabyteDB and where CBO fits in, and then go back and talk about how CBO works in a little more detail before jumping on to implementation details of the cost-based optimizer in Yugabyte and a small demo. The testing and the validation of CBO is a very critical challenge, so I'll take just a minute to talk about our testing framework called Taco, which we use to continuously test and improve the CBO. And then we go to the interesting part. I'll show you some benchmark results and then how to try out CBO for your own workloads. So what is a cost-based optimizer? So SQL, as you know, it's a descriptive language. That means the query describes how the result should look and not how it should be computed. And then it is the job of the CBO to find the most efficient execution plan for a query. I have here a very simple query. Here we are trying to find out all books from the science fiction genre and get the names of authors and publishers for this book. Now, you can imagine this query can be executed in multiple different ways. You could use index to apply this filter. You could sequentially scan the base tables, and you could have a whole permutation of join orders and join types, right? And so I've just illustrated a few possible execution plans for this query, and it would be the job of the CBO to look at statistics, to look at the data, and decide which one of these would be the most efficient execution plan. Now, this is a high level, like a software architecture of YugabyteDB. Yugabyte, as you know, brings the scalability and resilience of distributed systems to SQL databases. It does it by combining the Postgres query layer with a distributed storage backend that's derived from RocksDB. So in doing so, we are able to reuse a lot of the code and a lot of the components from these from Postgres and RocksDB. So, for example, here on the Postgres side, we are reusing the query compiler, the rules-based optimizer, the execution engine, and also major parts of the cost-based optimizer. However, our storage backend is much more complex and it needs to do a lot more work. For example, it needs to take care of replication, sharding, distributed transactions. And so the cost-based optimizer from Postgres doesn't reflect that entire complexity. And so we must adapt it to make it work for Yugabyte. It needs to reflect how Yugabyte storage engine works to make sure that it can properly estimate costs of execution plans and choose the best plan from that. And so diving a little deeper into how CBO works, this image here depicts 4 key components of the cost-based optimizer. As we saw in that query before, the search space for execution plans for a query grows exponentially with the number of join tables in that query, right? And so if you were to explore the entire search space, it's going to take a lot of time. So Postgres uses a dynamic programming based approach where it breaks down the problem into smaller pieces and it finds the best plan, like best sub plan for each piece of that query. And then it adds to that one more join table, and so it constructs a an overall execution plan for the query. Now, this is a simplified illustration of that algorithm on the left side. The how it computes the cost of each subplan is where the other three components come in. So first, it starts with statistics. So in Postgres, the database itself collects statistics for like all columns in all tables, such as number of distinct values, a histogram of the data distribution, and this on Postgres gets triggered automatically based on the amount of write activity on a table. And you can also trigger this manually using analyze command. These statistics are then used in selectivity estimation to compute the selectivity of a filter. So if you have a filter, how many rows will match this filter? And it uses the statistics to compute that. And then this selectivity estimates gets fed into the cost model, which is where we emulate the execution pipeline and we estimate the cost of generating that result. Now, fortunately, in YugabyteDB, we are able to reuse much of these components. So, for example, the plan search algorithm and the selectivity estimation do not need to change. For the analyze functionality, we had to implement a new way to fetch a random sample of data from .db, and we use the PG code to compute the statistics from that sample. So this functionality, the analyze functionality, has been available for a while now, although it needs to be triggered manually for now, and we are working on triggering it automatically in the future releases. And there is also work going on to optimize the performance of the analyze operation. So the other thing we had to fix was the cost model. And I explained before, we cannot simply reuse the cost model from Postgres. So early on, to keep things simple, what we did was we implemented a very simple cost model. We assigned heuristic per tuple costs to various operations. Like a sequential scan had a heuristic cost, an index scan had a heuristic cost, an index only scan had another heuristic cost. And then we used this to estimate the cost. So, and then we applied these costs to the cardinality estimates. Now, this has worked well in practice, especially for simpler use cases and simpler queries. So, but however, it doesn't model various aspects of the storage engine very accurately. And so it doesn't distinguish very well between collocated and distributed workloads, for example. And also, as we've gone and developed more optimizations in our storage backend, the complexity of our storage backend has actually increased, and it's becoming now harder to model that using just heuristics. So we had to go and develop from scratch a new cost model for the sequential scan and index scan of base tables. So here we have taken into a consideration various aspects such as the of our like storage backend, and then the network overhead and the network overhead in the network communication, and also we have modeled some optimizations such as the storage filter pushdown, and these help us estimate the cost more accurately. For operations such as joins, the data is fetched from docdb, and the join operation itself is executed on the Postgres execution layer. So fortunately, we didn't have to make much changes to the cost function for estimating the cost of a join. However, we've added new types of joins like a batch nested loop join, and we had to make some modifications to the nested loop join cost function to model this optimization. Now, since most of our changes are confined to the cost model, this design gives us the added advantage that we can easily upgrade from the PG version and utilize the advancements in other areas of the cost of the query planner. You can watch a recent YFTT talk from Arpan where he describes our project to upgrade the query layer from PG11 to PG15 for more details on that. So now let's get to talk about the cost models in the YugabyteDB. There is a lot of details to cover, and we won't be able to cover that in one talk, but I wanted to just show a glimpse of some of the most important features that we've modeled in YugabyteDB. Below, you see this image, which is a simplified illustration of how indexes and base table data is stored in Postgres versus in Yugabyte. So on the left, you see Postgres, like the row, when you insert rows into Postgres, they are written to the base table in the order of insertion on like here. And then all the indexes, the primary and secondary indexes, are stored separately and they are sorted B-tree data structures sorted on the key of the index. So every time you need to look up a key, you first need to look up the index and then find the CTID from there, and then look up the base table to find the matching row. And so the performance of primary index lookup versus secondary index lookup is nearly the same in PostgreSQL. However, on YugabyteDB, the base table itself is sorted on the primary key. Now, this is again a simplification. It's actually, the key is actually an encoded form of the primary key columns. And so basically what I'm trying to say is that it preserves the order of the primary key. So it's in the order of the primary key. And what that means is that the primary index is part of the base table. So it's a little cheaper to scan the primary index. A secondary index, like Postgres, is a separate data structure which is sorted on the secondary index key and points to the primary key. And now on a collocated database, the secondary index and base table data reside on the same nodes. But on a distributed database, the secondary index and base table data may reside on different nodes. So a lookup of a secondary index, like a secondary index scan, may be much more expensive because of the network overhead, because of another network round trip that is needed to fetch the base table rows. So these factors make primary index scan much more cheaper than the secondary index scan on YugabyteDB, right? And these we've modeled in the cost model to make sure that it makes a better choice between sequential scan, primary index scan, secondary index scan, or index only scan options. Now, another optimization that we've performed in that we have implemented in YugabyteDB is called storage filter pushdown. So I have a very simple query here. It's trying to fetch all books from the science fiction genre. So this query gets compiled on the Postgres query layer side. It gets compiled and passed to the execution engine. In the execution engine, Postgres would first try to fetch all the data from the disk and apply the filter. So what we do is we intercept this request of fetching tuples, and it gets passed on to a component called pggate, which translates this request to an RPC to the docdb. So docdb then returns all the results, and then the filter is applied on the execution engine. So this is how it used to work before this optimization was implemented. And as you can see, there is a lot of overhead due to bringing all the table, especially when most of it gets filtered away, right? And so we developed this optimization to push this filter down to docdb. And so in this case now, you push this filter down to docdb, and docdb must only send the rows that match this filter back to Postgres. And so this has led to significant performance improvements. And the way we've modeled this in the cost model is that we identify in the cost model the filters that can be pushed down to docdb. Then we compute the selectivity of just these filters and use that to estimate the number of results that we will pass from docdb to the Postgres query layer. And we use this to compute the network costs from that. I have a small example. I have screenshots here just for backup, but I'll jump to a live demo. I have here a simple table. There is a primary key on the column K. I create a secondary index on the column V. I will insert 1 million rows to this table. And now I have to analyze this table to collect statistics. And I will enable the new cost model by setting this GUC flag. So now the new cost model is enabled. Let's run a simple query with a range filter on the primary key K. So now, as you'd expect, the new CBO picks the primary index scan for this query, the plan using a primary index scan. It takes about 290 milliseconds. I'm going to run this query just a couple more times just to make sure this is the right time. So this is about 290 milliseconds. Now let's modify this query slightly and apply the filter on the column V instead. And so now when I run this query, the CBO picks the sequential scan plan for this query. And as you can see, this is a little slower than the primary index scan. One thing also to note is the filter. It gets pushed down to docdb as a storage filter. And so only the rows that are matching this filter are going to be returned to docdb. And our cost model takes that into account and decides that sequential scan would be a better plan than using a secondary index scan. But in fact, we can go ahead and try to force the CBO to use the secondary index using the PG hint plan extension. So I'm telling the cost space optimizer here, hey, you should use the secondary index for this query, and just let's see how it performs. So you see that this query now takes about 925 milliseconds when it's using the secondary index scan. So the cost model has identified that this is actually going to be a worse plan than sequential scan. So in fact, the old CBO, like the default configuration in Yugabyte today, would have picked the secondary index scan for this query. And that means this query would have run 1.5 times slower than in the new cost model. Now these errors, these performance issues, they can add up multiplicatively when you have a more complex queries with multiple join tables. And so this could result in much worse performance regression in a real life scenario. Now, going back to the slides, as I said, I can't cover all of the details, but I've mentioned here a list of all the things that we've had to model in the new cost model. We are going to we're going to publish a blog going out soon, which goes into a little more detail into some of these, and perhaps we will do future talks and blogs to also dive deeper into this part. Now I want to get to the validation. So as I said, testing the CBO is really challenging. So this is because, like, if you have a very simple query, it's easy to predict what would be the most optimal execution plan for this query and test for it. But if as the query complexity grows, then it becomes really hard to predict what would be a good execution plan for this query, right? And so it's very hard to test for that. And so that's where this framework comes in. We needed a lot of context to on CBO to get to this part, but this is actually something that we started working on even before we started working on the cost model, and this is really proven to be like a key to the whole puzzle. What this framework does is, for each query in the benchmark, it tries to force different execution plans using the PG hint plan extension, and this way it's able to verify whether the default plan that the CBO generated is indeed the best plan. And so this tool, we use this tool for continuously testing the CBO. Like every enhancement we make, we can run this with the Taco tool, and that would tell us how we are doing. And it will also take into account optimizations that are happening on YugabyteDB and tell us how we have to adapt the cost space optimizer for that. The tool also generates very insightful reports that have guided our engineering effort. So for example, on the right side, you see this graph that gets generated as part of this report. This is from a test that we had specifically, from benchmark that we had specifically developed to tune the cost model by isolating various aspects. So like a primary index scan, secondary index scan, and it's plotting the cost, the estimated cost of that execution plan versus the actual time. And as you can see from this graph, the cost correlates nicely with the time. And so this is how we are tuning the CBO. There is a very interesting YFTT presentation from Dimitri on Taco, and I recommend you to watch this if this is interesting to you. Now, getting to the results, we implemented a whole bunch of benchmarks for testing the CBO. And in most of these benchmarks, we are able to match the accuracy rate of PostgreSQL. What that means is we are able to get nearly the same number of best plans picked as Postgres. But to put CBO through its paces, we need benchmarks which reflect real life use cases. And so for that purpose, we've used two benchmarks here, TPC-H, the popular TPC-H, and the join order benchmark, which is derived from the IMDb data source. And so this chart is showing the percentage of queries for which the cost space optimizer picks the best plan. So one thing that jumps out here is Postgres also doesn't perform very well on these benchmarks, and so that's telling us that CBO is in fact a very challenging problem to solve. And the other thing it's telling us is that our Taco framework is really effective in testing the cost based optimizer, right? The other thing that is interesting here is that Yugabyte, the new cost model in Yugabyte, seems to outperform even Postgres, and this was quite surprising. And so we investigated this, and we found out that in some cases, it's in fact easier on YugabyteDB to find the best plan because network cost often overshadows the rest of the performance pipeline. And so if you get the network cost right, you will most likely end up with the most optimal plan. But that also tells us that getting the right plan on YugabyteDB is critical because the penalty of picking a wrong plan on YugabyteDB may be a little bit higher than Postgres.
So maybe one thing to just elaborate a bit, just so everybody's clear, is I think you mentioned we use essentially randomly generated hints, as in the Taco framework uses that to generate different plans, actually run them and compute the time. And then that's how we know what the best plan is. But maybe you can elaborate a bit on, I think you're going to cover it in the next slide actually, but whether a plan is the best plan or not, the difference may be very large or it may be very small in terms of the actual performance ratio. So that's where the percentage is only half of the story. And I think in the next slide, you're going to explain the other half of the story, which is the actual time between the optimal plan and the default plan that gets chosen.
Yeah, exactly. So let's with that go to the next slide. So that was just half of the story where we pick a better plan, but how bad were the bad plans? So this is a chart showing a histogram of number of queries and the speed up factor that we've achieved with each of these benchmarks. And so note here that the x-axis is on a logarithmic scale. And so what that chart tells us is that for join order benchmark, there were actually 3 queries where the new plan is in fact 1,000 times, more than 1,000 times better than the old plan. And the best speed up that we've observed on TPC-H is about 85 times. This chart also shows us some regressions. So you see some queries which are a little slower than before. Some of this is like variance between test runs, but we are tracking a few handful of actual regressions. In particular, there is this one query in TPC-H, which seems to run now 11 times slower. So the plan is now 11 times slower compared to before. This happens. So in many cases, these regressions are caused by mistakes in selectivity estimation, which is an issue that is known to affect Postgres. And it's not always very obvious how these issues should be fixed.
Yeah, and actually, if you see the question from Panay from YouTube, I think it's very much related to this. It's the question: do we collect additional statistics compared to Postgres for CBO? So it's actually very related to this particular query and this particular example. So maybe you can elaborate more on that.
Yeah, sure. So we haven't made changes to selectivity estimation, but we haven't yet also tested extended statistics, and perhaps that could help here. So in Postgres, you can use create statistics to collect extended statistics of correlations between columns, and maybe that can already help in making a better decision here. But yeah, I think that answers the question.
Yeah, I think it does. So the summary is that we don't yet, although we support the same thing as Postgres to create statistics manually. So I gather additional statistics, via manually using a create statistics statement. And we have discussed, based on observations we've had by analyzing various benchmarks, to implicitly automatically gather some additional statistics because they do help in certain situations. And I wanted to add one more thing on TPC-H, Gaurav, just we have a lot of different benchmarks in Taco. We've been iterating on a lot of them. Some of them are internals, others are based on queries by ORMs and kind of YSQL dump and internal queries. TPC-H is actually new. So this is a very honest kind of almost first workload analysis of our CBO is not something we have fine-tuned for months to get the TPC-H results. I think, or maybe you can share when we first run it, because it's something we actually did very recently, and this is essentially the initial result. And maybe you can share more on that.
Yeah, absolutely. So, in fact, join order benchmark is a very popular benchmark for testing the query optimizer, because this is more realistic data. And so we focused on join order benchmark. Here, there is like in join order benchmark data, there is like very diverse distribution patterns and correlations between columns. And this has actually been used in a number of research papers to test the cost base optimizer. And so this is what we've been testing on for a couple of months now. But TPC-H we only added to our suite, like I think 2 or 3 weeks before. And yeah, like you said, this is only the first results that we've achieved and we are showing here. Right. So in summary, that previous slide, we can summarize the speed up here. The speed up that is shown here is basically a ratio of the geometric means of runtimes of all the queries in the benchmark for the new cost model versus the YB default config as of today. So yeah, like you see here, we see much better speed up in join order benchmark, and that's particularly because the old cost model was doing the old CBO doesn't perform so well on join order benchmark, and yeah, and I suppose we will see improvements in TPC-H speed up as well. I have one more demo to show. So this is the TPC-H database. You can see this is the TPC-H schema here. Right now, we haven't run analyze, so we don't have statistics. So you see the PG stats view is empty, and also there is this is showing the number of rel tuples for each table, and this is showing 0. So right now we don't have statistics. So this is the default configuration of YugabyteDB today. Now, if I run this query, this is the query number 8 from TPC-H. As you see, this is not a very complicated query. It still has 7 join tables, and that makes it already quite challenging for the CBO to explore that entire search space and find the most optimal plan. I've already run this query and it's still running. So this is the old CBO performing, and let's see the plan that it comes up with. I suppose it should take about 22 seconds. Maybe let me.
Okay. Maybe pick the particularly worst plan now.
Yeah. So let me pick. Let me run this again.
So while waiting, maybe you can share the sort of the official results. I think you have
Sure.
a new cluster here with slightly different configurations, but I think on the slide you have the sort of official results from Taco with the standard configuration used there. So while we wait, maybe you can share that.
Yeah, right. So I have, like, for backup, just these numbers here. So this is the same query. What we found in the default configuration, that it takes about 16 to 20 seconds. We see, so this 16 seconds is coming from Taco runs, which uses a slightly different configuration than the demo instance that I'm using. Oh, by the way, the demo instance that I'm using is a distributed cluster with 3 nodes. Yeah, and so let me see if this finished now. Oh, okay, good that I have the backup slide. Yeah, so we saw this. The new cost model performs significantly better. This is almost 20 something times better, 25 times better. And the new cost model was now picking a better plan. And so that's why it's running much faster now. One thing also to note here is that even with the new cost model, our execution time is higher than Postgres. And that's because of 2 reasons. First, most importantly, PostgreSQL is using parallelization, which is a feature that we have been working on. In fact, Andre is going to talk next week in YFTT about our work on parallelization. This was not yet enabled for these tests, and this is something that we have modeled in the cost model, and we have to improve on. So we have to test and improve on that as well. The other reason why we are slower than PostgreSQL is also because we are using a distributed cluster, whereas Postgres is a single node. So this one completed. In fact, it took 73 seconds this time. Perhaps this is some issue with the node or something.
By the way, one question from YouTube again is there any planning time cost to using the new CBO? Does it take more time to do the planning with the new CBO, or is it a similar cost as before?
That's an interesting topic. So that's one of the things that we have to look for. The cost model needs to be not too complex to run. It needs to be performant, because the cost model is going to run for each subplan that's getting explored. So when your cost model is 10% slower, then your whole query planning time gets 10% slower. And so we have to find a balance between having a very simple cost model. And so we frankly haven't tracked it so well until now, but this is something that we focused on, and keeping the cost model simple and not growing it in complexity. But this is something we should be tracking. So going back to this demo, maybe perhaps let me try to see if the new CBO, new cost model does better. And so to enable the new CBO, once again, I have to run analyze to collect statistics. Now, if you see these, the PG stats, this one has the statistics for this table. This is just showing just one of the statistics, the number of distinct values. Here, the negative values are basically a negative of the multiplier of the total number of rows in the table, and that's showing us the distinct. So if it's a positive number, this is saying this column has 50 distinct values. If it's -1, it's saying all values in this column are unique. If it's -2, it's saying 20% of the values in this column are unique. And
since you're showing the statistics, and I think we're a little bit over time, but I wanted to make sure we also get to. There's a question from LinkedIn. Are there any recommendations on how often to analyze the tables? For example, if the table grows by 25% since the last analysis, should we reanalyze?
That's a very good question. Yes, you should run analyze frequently. We are working on triggering it automatically. That's an upcoming feature in the future releases. If I were to guess, I think 10% could be a threshold where if you have 10%, if your table has gone 10%, you should run analyze.
Thanks. And auto-analyze is a project that is well in the works, and I think it's going to be a future, not yet planned, but the future of YFTT platform as well. But yeah, until then, let's return to the demo, as we're a few minutes over, but I think we're very close to the end here.
Right. So yeah, the new cost model performs as I expected. So you saw I analyzed the tables and I enabled the new cost model. And now you see the plan that it takes about 740 milliseconds, which is still a little bit higher than the number I had in the slides. And that's perhaps because of a difference in configuration between what the Taco framework used and what I'm using here. Yeah, so that brings me to the most important slide, or most interesting one, at least. The real test for CBO can only happen in the real world, and we would like to invite you to try out the new cost models, and please provide us with your feedback so we can improve on it. Here I've just highlighted the steps you need. We recommend using a version 2024.1 onwards. You would need to run analyze to collect statistics before enabling the CBO. You can enable the CBO using either the GUC flag or G flag. And the last thing I want to also mention, we've developed a tool called CBO stat dump tool. So, and often debugging or analyzing issues with the cost-based optimizer is a really challenging. And so what we've done is we developed this tool which extracts minimum information needed to reproduce these issues on our test system. And so this includes TDL, G flags, and like statistics from the production deployment. With just this data, we will be able to reproduce the issue on our test systems. And by reproducing the issue, we are able to more effectively support you in giving you workarounds and also fixing the issues in future releases. You can use this link on the presentation to go to the GitHub project page for this tool, and perhaps we'll add a link to this tool as well.
Awesome. Thanks. Yeah, I think Gaurav, you mentioned there's also an upcoming blog. I think I don't know the exact date, but stay tuned for that. And if there's any questions we missed, please reach out to us either on GitHub or on Slack. I think we'll be ready to answer any further questions. And please give it a try on either the latest preview build or on the latest stable build 2024.1. So yeah, thanks Gaurav for an excellent talk, an excellent topic, and thanks everyone for joining.
Thank you so much. Have a nice day.